In another video, we introduced the idea of exsolution and immiscibility by looking at the system of orthoclase and albite. And so for orthoclase and albite, we had a solvus curve that looked like this, temperature on the vertical axis. So here's temperature increasing upwards. And if we had a bulk composition, let's say over here, and as it would cool, we'd have a single feldspar at high temperature, but it would break up into an albite-rich and an orthoclase-rich component, and those components would be more extreme in composition as we go to lower and lower temperatures. Well, we can make the same kind of diagram for the pyroxenes. So for the system, let's say enstatite and diopside, we can write enstatite over on the left, diopside on the right, and then we have temperature increasing upwards. So this is temperature. We would have a solvus where we could have something that looks like this. And so up here at very high temperatures, we would have a single pyroxene. It would be a complete solid solution between enstatite and diopside components. But as we go to lower temperatures, then these pyroxenes would break up into diopside and enstatite-rich components. Well, we're going to use these diagrams from the online textbook by Dexter Perkins on mineralogy to see how we can evaluate these systems when we add a third component, wollastonite. Well, we're going to look at three components: enstatite, wollastonite, and ferrocylite. The wollastonite is actually only of minimal interest to us because it's really not a true pyroxene. It is a pyroxenoid. There is no solid solution between wollastonite and the regular pyroxenes down here. So these are the true pyroxenes off here in the bottom part of this diagram. The wollastonite structure has highly twisted chains, and we have rather straight chains over here. So the pyroxenes, you can draw it really quickly. You can think of tetrahedra as making these very straight chains, and we have a diagram like this that we discuss in another video. The chains are very twisted here, and it limits solid solutions, so that we don't really care about the upper part of this diagram when we're dealing with pyroxene. So for that reason, a lot of times we talk about the so-called Pyroxene Quad, the quadrilateral, the four-sided figure that just connects diopside, hedenbrigite, ferrocylite, and enstatite, which we're showing also here in this diagram from Dexter Perkins. Well, this area here is the so-called Miscibility Gap, and it's labeled that over here as well. So this area in blue, the way Dexter Perkins has drawn it here, the area in blue is the area where we have solid solution. We'll just write SS, and then we have solid solution up here in this calcium-rich part of the diagram. And so the way that this would relate to this diagram over here is that if we were to look at the enstatite-rich side of the diagram, so let's say, let's say this is enstatite plus ferrocylite, and let's say this is diopside plus hedenbrigite. We don't have to have just purely magnesium calcium end members. So this enstatite ferrocylite part here would be this part of the diagram here, where we would have complete solid solution where we haven't hit the solvus. And then in this part of the solid solution here between diopside and hedenbrigite, that would be this part of the solvus over there where we have a bulk composition that would not hit the solvus no matter how far we cool it. So we got a bulk composition here that would not hit the solvus curve, and another one over here that would not hit it. But if we had a composition that was something in between, like here, then at lower temperatures we would hit that solvus, and that composition would break up into a calcium-rich and magnesium plus iron-rich component. And that vertical line that I've drawn here would be analogous to that horizontal line that we have drawn over there. So this represents that miscibility gap. Oh, that should be a P, not a B. So that would be the miscibility gap that we would have shown already. We give for the orthoclase albite case, and then we've drawn over here for enstatite and diopside. Over here is a little more realistic look at the system. So we have a miscibility gap shown for the case of temperatures of 800 degrees centigrade and 1 atmosphere. So we have complete solid solution that is very limited. We'd have a very, very narrow amount of solid solution between an enstatite ferrocylite rich component and let's say diopside-rich components, we might have pyroxenes. If we have two pyroxenes in a system, and it's possible many rocks do crystallize two pyroxenes at 800 degrees, the augite and the orthopyroxene compositions would be very far apart from one another. But if we were to increase the temperature to, let's say, 900 degrees, we might have a miscibility gap that's quite a bit narrower. So I'm just going to draw it, this is really schematic here. Let's call it 900, 950 degrees. Then the separation between the clinopyroxene or augites on the one hand, so the augites, these are the same as our clinopyroxene, we'll just write as CPX, orthopyroxene is OPX. The separation between those two would be lower. So the smaller the gap between these two kinds of pyroxenes, CPX over on the calcium-rich side and OPX on the iron-magnesium-rich side, the smaller the separation, then the higher the temperature. So just like in the orthoclase albite system, we can use these kinds of compositional separations as a thermometer. We don't get the very coarse perthite-like textures in pyroxenes, but under a microscope you can often still see this kind of exsolution, this kind of unmixing. If you start with a composition that's at very, very high temperature, let's say at 900 degrees or maybe even higher at 1100 degrees, and then it starts separating into something that is much more compositionally distinct at lower temperatures. So this is an analogous system with pyroxenes. We usually show them in the case of this Pyroxene Quad rather than the binary diagram here, because this quadrilateral case shows us a more complete look at the pyroxene components that are being mixed or unmixed, as the case may be.